Hello, and welcome to Sleepy Math. Whether you're here because you want to learn, relearn, or just listen to something as you're trying to relax and fall asleep, I hope you'll enjoy this little lesson that I have for you on domain and range of functions. For the record, I am a math teacher. I do a lot of things. I do computer work as well, but my primary position is as a math teacher. So let's look at domain and range. So I have a little trick that I like to share with my students that compare domain and range. Because a lot of people tend to forget which one is which. The domain tends to be the x values, and the range tends to be the y values. Now it depends on which variables are being used, but this tends to be the case just generally speaking. Domain happens to also be my input values, and that is the important part of domain and range. Range, therefore, would be my outputs. And the way that I teach my students to remember this is that if you look at domain and range, they are in alphabetical order. X and Y are in alphabetical order. Input and output are in alphabetical order. So why do domain and range ultimately matter? Well, let's consider you have a job, and at that job you make $20 an hour. And on a given day, your boss tells you that you may be needed up to 4 hours. It's also possible you might not be needed at all. So let's say 0 to 4 hours. At this particular job, you get paid for the full hour regardless of how much of the hour that you work. So if you show up and work for 1 second, you get an hour. If you show up and work for 59 minutes and 59 seconds, you get paid for 1 hour. As soon as you hit 1 hour and 1 second, that's when your second hour comes into play, and so on all the way to a maximum of 4 hours. This is an idea of discrete quantities, 0, 1, 2, 3, and 4. So our domain, our possible inputs to determine how much money we can make at this job, is 0, 1, 2, 3, and 4. Pardon my curly braces. They are particularly difficult to draw with my finger on this whiteboard, not that I have great handwriting anyway. So those are the possible inputs. My outputs then are to take every possible input and determine what the output would be. This is a very simple function, which I can actually write off to the side here. I can think of it as f of x or y is equal to 20x, $20 per hour. So if I work 0 hours and decide not to go in this day, or the boss doesn't need me, I make $0. If I work 1 hour, I get $20. If I work 2 hours, I get $40. 3 corresponds with $60, and 4 corresponds with $80. So I have 5 possible inputs, and each input corresponds to 1 possible output. Now, we can also consider the idea of continuous values. This is a case of discrete. Let's say after we work, we decide we want to use some of our money to buy some broccoli at the store. And broccoli costs $1 per pound. Let's change that to $2 per pound. To $2 per pound. Sorry for using the imperial system and not the metric system. So $2 per pound of broccoli. And once again, the store has 4 pounds available. So we could look at the broccoli and say, you know what, we don't really like this broccoli. We're not going to buy any broccoli. So 0 is the minimum amount of broccoli that we could buy. And they have 4 pounds. We could buy all 4 pounds. So my possible inputs are the values from 0 to 4. I can't have less than 0. It doesn't make sense to have negative broccoli. And I can't buy more than 4 because they don't have more than 4 pounds to give me. And therefore, my possible input values, or my domain, is from 0 to 4. So if I identify that, now I don't really have a great use for curly braces. There is something called set builder notation, and it's kind of a fancier way of what I'm going to put down here. But I think for our purposes to just understand what the domain is, we have all values of x such that x is less than or equal to 0. 0 is less than or equal to x, which is less than or equal to 4. So that's all possible input values. I could buy 0 pounds, 4 pounds, 2.371695 pounds. I could buy pounds of broccoli. Now, technically, if you were to actually go to the store and you were to weigh the broccoli, most stores tend to weigh to the nearest hundredth. And therefore, we are still talking about discrete values. However, I feel that we would be nitpicking to consider this a discrete value, and it would take a very long time to consider the cost of 0.01 pounds of broccoli, 0.02 pounds of broccoli, and so on. For the range now, rather than trying to figure out every possible input because we have infinite inputs, we now have to figure out the continuous range of our outputs. Because this is a linear function, because the rate of change is consistent or constant, we can simply figure out the corresponding range at 0 and the corresponding output at 4. So at $2 per pound, if I buy 0 pounds, that's 0, which will be less than or equal to y, which will be less than or equal to, well, 4 pounds would cost $8. And hopefully that all makes perfect sense, because 0 pounds of broccoli should cost $0 and 4 pounds of broccoli cost $8, and all the in-betweens for our input correspond with all the in-betweens for this output. However, when dealing with nonlinear functions, we can't actually do that. So let's say hypothetically I had a function, and I'm going to call it y, and it's going to be equal to negative x squared plus 2x. That'll be good. Negative x squared plus 2x. That's my function. And I just want to go from 0 to 2. And if I plug in a value of 0, I get y is equal to, well, negative 0 squared is 0, plus 2 times 0 is 0, that's 0. And that's when I plug in 0. So for x equals 0, I get that y is equal to 0. And if I plug in this value of 2, then y is equal to, well, negative 2 squared is negative 4, plus 2 times 2, which is 4 again. So negative 4 plus, I'm at 0 again. So when x is equal to 2, y is equal to 0. Now, does it make sense that the range, even over this restricted domain from 0 to 2, that the range would simply be 0 or 0 to 0? Well, it doesn't make sense. And we can discover why it doesn't make sense very simply by saying, well, what happens when y is equal to, I should say when x is equal to 1? Y is equal to negative 1 squared, which is negative 1, plus 2 times 1, which is 2, and we get an output value of 1. So if an output of 1 happens somewhere in our domain from 0 to 2, then the range certainly can't be 0 to 0. Here's where it might make sense to look graphically. So if I were to look at a little graph, and we said y is equal to negative x squared plus 2x. Sorry, I didn't leave myself enough room to make that look nicer. And we happen to note that we had a 0 at x is equal to 0. And we also had a 0 at x is equal to 2. These are the roots of our function. Negative x squared plus 2x, this is a quadratic function with the negative leading coefficient, and therefore it is a downward-facing parabola. And with this sketch, we can see y It doesn't make any sense to just take the starting and ending values when dealing with nonlinear functions. Now, there are other exceptions to that rule. For example, if we had an exponential function, let's go with y is equal to 2 to the x power. If you recall, exponential functions start very close to 0, start to grow, and then start to grow even faster. Or potentially you have an exponential decay function. However, with exponential functions, the value of the function is either consistently increasing or consistently decreasing. There is no change in direction. Therefore, if we were to say, choose a range, I should say a domain of from, how about, oops, I didn't mean to do it that way. Let's say -1 is less than or equal to x is less than or equal to 3. In this case, it would be perfectly okay to say, well, for my range, when I plug in an x value of -1, 2 to the -1, recalling our negative exponent properties, the -1 power is the same as 1 over 2 to the +1 power, or it's just simply 1/2. And that will be less than or equal to y, which will be less than or equal to, well, what's the value when x is equal to 3? 2 to the 3rd power, or 2 cubed, which is 8. And because there is no change in direction, we know that 1/2 is the smallest value in our range, and 8 is the largest value in our range. That's it for today's lesson. I hope you enjoyed. If your goal was to fall asleep, I hope you fell asleep. If your goal was to learn or relearn something, I hope you enjoyed, and I hope you'll take the time to both like and subscribe to my channel, and I hope you'll check in next time as well. Goodbye. Hello, everybody. I don't know about you, but I had quite a rough day. And you know, there's nothing that's going to make me relax quite like doing a little bit of trigonometry. So let's talk about one of the things that I know best about trigonometry, and that is Pythagorean triples. Pythagorean triples. Now, likely you've heard of these before. If not, these are 3 integers, positive integers that is, that fit the Pythagorean theorem. Now, the formula associated with the Pythagorean theorem, as you probably recall, is a squared plus b squared is equal to c squared. Now, there's a lot to be said about this, but I won't waste your time. I want to get into Pythagorean triples. The most simple Pythagorean triple is what's known as the 3, 4, 5 triple, meaning if I plug in 3 for A, and 4 for B, and 5 for C, I can show that the Pythagorean theorem holds true. 3 squared is, of course, 9, 4 squared is 16, 5 squared is 25, and 9 plus 16 is also 25. So 3, 4, 5 is a Pythagorean triple, as those integers fit the Pythagorean theorem. There are several others, 5, 12, 13, for example. And we can show that 5 squared plus 12 squared is equal to 13 squared. 25 plus 144 is equal to 169. And 25 plus 144 is 169. Now, these are just two, I would say the two most basic Pythagorean triples that we have. How many Pythagorean triples are there? Probably infinite. I don't know if it's ever been proven that it is definitely infinite, but it's certainly more than you could ever possibly need. So, how do we figure out what the Pythagorean triples are? Well, there's a pretty cool little formula for that. Now, for any Pythagorean triple, all you need are 2 integer values, both positive, s and t. So s and t are elements of the set of integers, and also we're going to say that s is greater than t. Now, with this being the case, we can generate 3 values. One is going to be s squared plus t squared. I'm not putting that in parentheses. I'm going to have a second value of s squared minus t squared. Oops, I wrote a 2. S squared minus t squared. And the last one is just going to be 2st. So if I pick two values, I'm going to go with 4 and 1. So if s is 4, we get 4 squared plus 1 squared. We get 4 squared minus 1 squared. And we get 2 times 4 times 1. That doesn't look very good, and we can do better. So if we can do better, we should do better. 2 times 4 times 1. 4 squared plus 1 squared, that's 17. 4 squared minus 1 squared, that's 15. And 2 times 4 times 1 is 8. So in reverse order, we are implying that 8, 15, 17 is a Pythagorean triple. Well, first let's check it. 8 squared plus 15 squared is equal to 17 squared. 8 squared is 64. 15 squared is 225. And 17 squared is 289. 64 plus 225 is 289. So we can show that 289 is equal to 289. So it worked. Why does it work? Well, here's where we get a little bit heavier with how we look at things. So I told you that the three values are s squared plus t squared. And we also have s squared minus t squared. And we have 2st. Now this top one, that's always going to be the biggest values. So when we square all three of these two are going to be the ones that we end up adding. So let's see if we can create a proper formula. 2st, one of the smaller values, squared, plus s squared minus t squared, squared, is going to equal s squared plus t squared, squared. If I square my very first term that I have here, I wind up with 4s squared t squared. For the next part, I have a binomial that's being squared. So what we wind up with is s to the 4th minus 2s squared t squared and plus t to the 4th. Zoom out to give myself a little more room here. So s squared plus t squared squared, what that's going to wind up being is s to the 4th. I can make that look better. S to the 4th plus 2s squared t squared plus t to the 4th, just by expanding that binomial. I would like to leave the right side alone. So let's operate on the left side. You'll notice I have an s to the 4th. I have this was supposed to be t to the 4th. My apologies. This one I'm not going to make look better. That's a 4 now. I have a plus t to the 4th. And I have 4s squared t squared and minus 2s squared t squared. Those are like terms. And when I combine those, 4 minus 2 is 2. So what I wind up with is s to the 4th plus 2s squared t squared plus t to the 4th. And that equals, well, look what I already had on this side. S to the 4th plus 2s squared t squared plus t to the 4th. Same thing on both sides. So this implies that this would work for any s and t, even if they were not integer values. And while that is true, generally speaking, when we're talking about Pythagorean triples, we are talking about Pythagorean triples in regards to integers, though there is a case to be made for certain decimal values as well. Certainly, if we were to scale a Pythagorean triple and instead use something like 0.3 squared plus 0.4 squared. That would give us 0.5 squared, or 0.09 plus 0.16 is equal to 0.25, and that is also true. The last thing to say about this is the idea of the primitive Pythagorean triples. When I gave you the conditions for using that formula, I only said that s and t needed to be integers and that s needed to be greater than t. Well, there are two other conditions that are often used, and the first is that the greatest common denominator between them, so g, c, d, of s and t, must be 1, meaning they are co-prime. Not necessarily either one of them is prime numbers, though certainly they can be, but they must not share any factors in common in order to be a primitive Pythagorean triple. The other thing is that s and t have different parity. I'm just going to abbreviate here, different parity. I'm spelling that correctly. And all this means is one is odd, one is even. It doesn't matter which is odd and which is even, but one must be odd and one must be even. So let's take a look at an example where maybe these conditions aren't met and compare them to a situation where these conditions are met. So I would like to use 4 and 2. So if I use s is equal to 4, my values then are 4 squared minus 2 squared, 2 times 4 times 2, oops, I wrote a t, and 4 squared plus 2 squared. So 4 squared minus 2 squared, that's 16 minus 4, or 12. 2 times 4 times 2, that's 16. And 4 squared plus 2 squared, 16 plus 4 is 20. So 12, 16, and 20. 12 squared is 144, 16 squared is 256, 20 squared is 400. So of course, those work out. I apologize for not showing, but I wanted to leave room to show what happens if we just divide all of these values by 4. 12 divided by 4 is 3, 16 divided by 4 is 4, and 20 divided by 4 is 5. 3, 4, 5 is a primitive Pythagorean triple, whereas 12, 16, 20 is just a multiple of this primitive 3, 4, 5. How do you get 3, 4, 5? Well, instead of using 4 squared and 2 squared, let's cut each of those in half. 2 squared minus 1 squared. 2 times 2 times 1, and 2 squared plus 1 squared. We get 3. 2 times 2 times 1 is 4. And 2 squared is 4 plus 1 squared is 5. And that's where 3, 4, 5 comes from. Well, I hope you learned a little something today. I hope you were able to relax. I hope that the background sounds weren't too distracting as they were to me. If you're still awake, please like and please, please, please subscribe to this channel. And if you're asleep, good for you. I hope you sleep great and you wake up tomorrow feeling refreshed and maybe just a little bit smarter. Well, until next time, keep on mathin'. Good evening, or good day if you're watching this during the day. It's time for another episode of Sleepy Math. Today, I'm going to talk about one of my favorite things, cosine. I do love all trigonometry, but cosine is my favorite. The law of cosines, the uses of cosines, and frankly, just the sound of it, cosine. So let's look at what cosine is. What you hopefully remember is that cosine is one of the 3 basic trigonometric ratios, and most likely you learned in school from this. So, ka, toa. Or if you had a particularly cool teacher, some old hippie caught another hippie tripping on acid. Regardless of the mnemonic device you used, ka is what we're focusing on today, and this means that for any given right triangle, that the cosine of a non-right angle is equal to the length of the adjacent side divided by the length of the hypotenuse, CAH. But that's a pretty basic and straightforward use. Much cooler than that, in my humble opinion, is the law of cosines. And the law of cosines is this. C squared is equal to A squared plus B squared minus 2AB times the cosine of C. That's not the best O I've ever seen, but it's going to do. Now you may notice that this part, if I remove that, that may look very familiar, especially if you watched the last video of Sleepy Math. It's basically the Pythagorean theorem. Well, the Pythagorean theorem is actually just a very special case of the law of cosines, and I will show that in just a moment. First, let's undo our scribble. So the way the law of cosines works is if I have a non-right triangle, although it does work in right triangles as well, and I'm going to label the three vertices A, B, and C, and I can label the sides opposite those vertices with the lowercase counterparts, lowercase a, lowercase b, and lowercase c, we can actually form a relationship between those three sides and the angle at C. And that relationship is the equation that you see above. Let's see it in action. So if I were to have a triangle like this, and we're going to make this nice and easy, and I'm going to call this angle here 60 degrees. And I'm going to try and find the side opposite that. If I happen to know that this is 3 units and this one is 4 units, then I can use the law of cosines. I'm looking for the unknown side, which is opposite a known angle, and both sides that come off of that angle have known lengths. So what I can say then is that x squared is equal to 3 squared plus 4 squared minus 2 times 3 times 4 times the cosine of 60 degrees. I really didn't leave myself enough room there, so I'm just going to note that the cosine of 60 degrees is 1/2. So let's just fill that in now. Therefore, x squared is equal to 9 plus 16 minus, well, my 2 and my 1/2 cancel each other out, so all I'm left with is 3 and 4, so times 12. 9 plus 16 is 25, minus 12 is 13, so x squared is equal to 13, and therefore x is equal to the square root of 13. Obviously, I don't need to account for plus and minus, because there's no such thing as negative 13 when we're talking about the length of a side of a triangle. The law of cosines has many, many, many uses. I'm of course not going to go into every single one of them here, but first let's get back to what I was talking about when I said it's really, the Pythagorean theorem is a special case for the law of cosines. So let's draw another triangle. This time it's going to be a right triangle, and we are going to say that maybe we're trying to find, that's going to be my C right there, and let's say I'm trying to find x, and this is going to be 3, and this is going to be 4. Looks pretty similar to my last triangle, right? The only difference is we're using a 90-degree angle instead of a 60-degree angle. So it's going to start the same way. The x squared, the unknown, is equal to 3 squared plus 4 squared minus 2 times 3 times 4 times, and I left myself enough room here this time, cosine of 90 degrees. 90 degrees. Well, what is cosine of 90 degrees? If you have a calculator handy, which you shouldn't, you're trying to relax here, but as long as you're in the degree setting and not the radian setting, if you are in radian, you can choose to use pi over 2 instead. But cosine of pi over 2 or cosine of 90 degrees is 0. So this becomes negative 2 times 3 times 4 times 0. And anything times 0 is 0. So all we're left with is x squared is equal to 3 squared plus 4 squared. Now you may remember that's got to be 5 squared because of Pythagorean triples, either from my past videos or your own memory. Or we can do the math on it and say that x squared is equal to 9 plus 16, which means x squared is equal to 25, and therefore x is equal to 5. So there it is. The law of cosines can work on right angles as well, but really that's just the equation associated with the Pythagorean theorem. Another use for cosine is when we start talking about vectors. So there is a formula for how to find the angle between two vectors. And this one is a little bit tricky, if you've never used it before anyway. So basically what it comes down to is that the cosine of an angle between two vectors is equal to the dot product of the two vectors. Oops, I was supposed to put u first. Let's change that. My u's and my v's are going to look pretty similar anyway. The vectors u and v, it's their dot product divided by the product of their magnitudes. Now the dot product, if you don't recall, is what happens when you multiply the x values of both vectors, and to that you're going to add the y values of both vectors. If you were doing three-dimensional vectors, you would also include the z values. The magnitude is simply the length of the two vectors, and that can be found using the distance formula, or ultimately the Pythagorean theorem that we just used. So let's take an example here. Let's assume that we have two vectors, and we are going to say that vector u is the vector 2, 3, and we are going to say that the vector v is, let's go with 1, -2. So now I have my two vectors. To use the law of, or I shouldn't say the law of cosines, I should say to use this formula to find the angle measurement, first I need to take the dot product, which means I'm going to be multiplying 2 times 1 and multiplying 3 times -2 and adding those two things, because that is how we find the dot product. So 2 times 1 is 2, plus 3 times -2 is -6. And we are going to divide that by the magnitude. So the magnitude says for u, I'm going to take 2 and I'm going to square it, and I'm going to take 3 and I'm going to square it. So that's 13, so we get radical 13. And I'm going to do the same thing with v. So I have 1 and I have -2. 1 squared plus -2 squared, that is going to be radical 5. I don't know why I had written that plus there. That is incorrect. So times radical 5. So what we wind up with is -4 divided by the square root of 65. Now keep in mind, it is the cosine of this angle, which is equal to -4 over the square root of 65. And therefore, what I really need to do is say that theta is equal to the arc cosine of -4 over the square root of 65. I don't happen to have a calculator handy, so while I can say that the angle between the two measures is exactly the arc cosine of -4 over the square root of 65, if you would like to know the degree or radian approximation, you may have to bust out your own calculator and do the math on that. Well, I was thinking of trying one other thing, but I'm afraid that's all the time we have for today. Hopefully you're asleep by now, but if you're not, please feel free to leave a like and maybe think about subscribing, and perhaps even sharing this video with your friends. So long. Good evening, all. In this episode of Sleepy Math, we are going to take a look at the 16-point unit circle for trigonometry. Now, the 16-point unit circle is a very useful tool, and basically what it comes down to is it is a circle with a center at the origin and a radius of 1. You can probably draw a better circle than I can. At least I certainly hope you can. If you can't, that's okay. I'll draw a better one for the next circle that we're going to use. The idea is that any point on the circle can be connected to the center and form a radius, like you're seeing right here. And you can drop a perpendicular to the x-axis from wherever that point happens to be, creating a right triangle. The coordinates of the point then are going to be cosine of x for the x value. I should say cosine of theta, silly me. Theta is going to be our angle. So x is cosine of theta, and y is sine of theta. And this is also has something to do with polar coordinates. Anywho, so we have cosine of theta is our x value, sine of theta is our y value, and the reason is if I kind of break this triangle out, take it outside of the circle, we have the hypotenuse, which is 1. The reason it's 1 is that this is the unit circle. There's 1 unit for a radius. And if this is theta here, then I have an adjacent side, and, oops, I wrote hypotenuse. I didn't mean to. I meant to write O for opposite. So we have an adjacent side and an opposite side. Well, sine of theta is equal to the opposite over the hypotenuse. So sine of theta would be O, which, if we go back to where our actual triangle is, that's how far above or below the x-axis it is. That's my y value. Likewise, cosine of theta is adjacent over the hypotenuse, or just A, because it's over 1, and that's going to correspond with the x value. How far left or right of the y-axis does the point lie? Now, for the 16-point unit circle, the idea is there are 16, I'll call them critical points, that one could know in a unit circle. These are the ones that are worth committing to memory, if you will. Mostly we are going to work in the first quadrant. That's the upper right. The second quadrant is our upper left. The third quadrant is our lower left. And our fourth quadrant is our lower right. The thing is, in the first quadrant, everything's positive. So that's where we want to do all of our work. Any angle that ends up in one of the other quadrants, we will use our first quadrant as a reference. I'll explain that later. So let's start. We have 0. We have 90 degrees, which I'm going to call pi over 2, because I think radians are cooler than degrees. And then we have pi. We have down here, I don't have a ton of space. I can zoom out a little bit though. There we go. Down here we have 3 pi over 2, which is the same as 270 degrees. And then when we get back to 0, that's also the same as 2 pi. I'm not going to write that in. In the first quadrant, in addition to the quadrant angles that we have of 0 and pi over 2, I want to draw 3 more. 1 corresponds with 45 degrees, 1 corresponds with 30 degrees, 1 corresponds with 60 degrees. I'm not using a compass, so these probably aren't exactly correct, and that's okay. In radians, what we have here is pi over 6, pi over 4, and pi over 3. So those are the 5 angles, really, that we want to work with, and everything else will be some sort of reference. We have 0, pi over 6, pi over 4, pi over 3, and pi over 2. Before I go to what the values are, because I'm going to have to draw these on a separate angle, I just want to illustrate how I would actually work with some other angle. So let's say hypothetically I had an angle that was, let's call it 5 pi over 6. That's going to be here. So 5 pi over 6. What I would do is I would note that the angle from here to here is the same as the angle from here to here, except reversed. The angle between 0 and pi over 6 is the same as the angle between pi and 5 pi over 6. The difference in radians is pi over 6. So whatever my x and y are, at pi over 6, I'm going to use the same things over here in my second quadrant. You'll notice the y value is the same. How far above the x-axis am I? The x value, however, is going to be the negative. It's a mirror image, so negative x. And that's why we use reference angles, because it's very easy to just change the things between positive and negative depending on whether x is positive or is negative. So we can always reference our first quadrant reference angles. Okay, let us make another circle. And this time, instead of putting the angles down, I'm just going to put what the x and y coordinates are. So our quadrant angles, those are pretty easy. 0 corresponds with 1, 0, x value of 1, y is 0. Likewise, if I go to pi, it's going to be negative 1, 0. Let's make that look more like a comma. For my pi over 2 and my 3 pi over 2, I'm going to have 0, 1, and 0, negative 1. Those are my 4 quadrant angles. Now, the next 3, if you already have them memorized, awesome. This is just a refresher for you. If not, you may find that I am going to have a little trick for you that's going to help you remember them. Right now, I'm just going to tell you what they are, and then later we'll make a chart for how to remember these things. So, this corresponds with pi over 6. This is 30 degrees. Cosine of 30 degrees, or pi over 6, is radical 3 over 2, and sine is 1/2. Zoom in a little more so I can draw this a little easier. I'm actually going to jump up to 60 degrees now, because what's great about 60 is we just reverse the two. Sine and cosine basically switch places. So cosine of 60 degrees, or cosine of pi over 3, is 1/2, and the sine of that angle becomes radical 3 over 2. And then we just have this one that's my pi over 4, or 45 degree angle. And for those, x and y are equal to each other, which I would say is of interest. And in both cases, it's radical 2 over 2. I can make a better 2 than that, and therefore I will. Much better. Now, if you're curious, go ahead and apply the Pythagorean theorem on all of these. If you square the x values and you square the y values of any one of these points, add them together, you will get 1, the square root of which is 1. And hopefully that makes sense, because every single point that we put on this unit circle can ultimately be turned into a right triangle, and the Pythagorean theorem should hold true for all right triangles. Okay, so that's really what you need out of a 16-point unit circle, even though I did not put in the other, 9 points. You can also do these on your own if you want. It's all the same values, just some of them are negative. And I'll leave that to you to figure out. So that's 16 points all the way to the unit circle. Those are the ones that you really should either have memorized or be able to easily reference. Now, when it comes to memorization, how do we remember what's what? Well, it's actually pretty easy, at least for sine and cosine. Tangent may be a tiny bit trickier, but if you remember that tangent is the sine divided by the cosine, then that actually becomes pretty easy as well. So what I'm going to do is I'm going to make a chart, and the chart is going to have the angle, the sine of that angle, and the cosine of that angle. We're only going to go from 0 to pi over 2. So we're going to go 0, pi over 6, pi over 4, pi over 3, and pi over 2. I'm not going to draw the lines in between them. If you want, you can write the degrees next to yours on your chart, or if you're just following along and trying to fall asleep, hopefully you're not writing anything and you're just watching what I'm doing. So sine of 0 is 0. Cosine of 0 is 1. Sine of pi over 6 is 1/2. Cosine of pi over 6 is radical 3 over 2. Sine and cosine for pi over 4 is radical 2 over 2. Sine of pi over 3 is radical 3 over 2, and cosine is 1 over 2. And finally, sine of pi over 2 is 1, and cosine of pi over 2 is 0. Now, I think it's pretty obvious that sine and cosine are the same pattern, just in the opposite direction. We go 1, radical 3 over 2, radical 2 over 2, 1 over 2, and 0. So cosine is consistently decreasing between 0 and pi over 2. And sine goes from 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. So sine is increasing from 0 to pi over 2. Now, how do you ultimately remember that? Well, I'm only going to show you this once, and just know that it applies both forwards and backwards. What I'm going to do is I'm just going to write a bunch of things over 2. Let's give myself a little more room here. Tiny bit more still. Okay, and now I'm going to write 0, 1, 2, 3, and 4. Because if I just do everything over 2, that's a pattern. 0, 1, 2, 3, 4, that's a pattern. And now what I'm going to do is I'm going to put a square root over the numerator of every single one of these. And then I'm going to note what they're equal to. Because the square root of 0 is 0, so 0 over 2 is 0. The square root of 1 is 1 over 2 becomes 1/2. Square root of 2 is irreducible, so we'll keep that as square root of 2 over 2. The square root of 3 is irreducible, that's the square root of 3 over 2. And the square root of 4 is 2, 2 over 2 is 1. And would you look at that? 0, 1/2, radical 2 over 2, radical 3 over 2, and 1. That exactly matches what we put in for sine. Cosine is just the reverse. Well, that's it for today. I hope you enjoyed. I hope you're asleep. And if you're not asleep, I hope that you'll subscribe and perhaps tell your friends about this. Have a great night.